All right. So today we'd like to ask what happens if the spectrum of the system is continuous. And to try and understand this, we're going to be studying a free particle on the real line. The Hamiltonian for the free particle is given by the second derivative operator. The minus sign there is there to make sure that we have a positive spectrum of states. So the energies come out to be positive, and we want to consider the particle on the whole real line. But to consider the particle on the whole real line, I have to do integrals over the real line. And to make sure that my integrals are convergent, what I'll do is I'll take the interval from minus L over 2 to L over 2. So this is an interval of length L that goes from minus a half L to a half L. And then at the end of the day, we'll send L to infinity. Now, it's not too difficult to see that eigenfunctions of this operator are given by plane waves. So just complex exponentials, e to the ikx. And if I act on e to the ikx with the second derivative operator, every time I act on it with a derivative, it pulls down a factor of ik, pull down two factors of ik, and you'll get a k squared. This minus sign is precisely there to make sure that this k squared comes out to be comes out of the plus sign. In other words, we identify here the eigenvalues of the system with k squared, and this is why we call it a continuous spectrum. It's precisely because the k values are a continuum of values, unlike in the case where the spectrum was where the spectrum was discrete. I could label it by some set of integers n. So that was easy enough. We just guessed an eigenstate, and we acted on it with the derivative operator, and we were able to read off what the eigen values corresponding to those eigenfunctions are. So now let's impose some boundary conditions on the problem, right? And in particular, I'm going to take this interval from minus L over 2 to L over 2, and I'm going to identify it. So I'm going to take the real line and put it on a circle. So we're now going to consider a quantum particle on a circle, which is basically imposing periodic boundary conditions on the system. So now let's impose periodic boundary conditions and the periodic boundary conditions we want to impose are that phi, our particle wave function, labeled by this k eigenvalue at minus L over 2 is the same as phi k at plus L over 2. Okay? And if I substitute in the expression, the complex exponential for phi, this tells me that e to the minus I k L over 2 must equal to e to the plus I k L over 2. Or in other words, that e to the I k L is equal to 1, and e to the I k L is equal to 1 if and only if k L is equal to 2 pi n. So this imposes a constraint on the values that k can take to have periodic boundary conditions, right? Namely, that k must be of the form 2 pi n over L, where n here is now some integer that I'm going to use to label the k's. So taking the system on the real line, imposing periodic boundary conditions so that that real line is then identified with a circle, constrains the possibilities that the eigenvalues can take, right? From any old eigenvalues to eigenvalues that are of the form 2 pi n over L for some integer n. And associated to this is a corresponding eigenvalue, eigenfunction that I can normalize. So with normalized eigenfunction, let's call them chi. So chi n of x is 1 over root L e to the I k n x. And as a quick calculation, in class exercise, if you want, for you guys, I'd like you to, so a quick calculation, compute the normalization factor. Remember what I said, that my classes are typically peppered with these quick calculations that I'll put down in red. All of them are fairly straightforward. They're easy enough to do. You can do them on the fly, or you can check them after class when you're putting together your notes. And they will really, they're just little calculations that you ought to do to convince yourself that whatever I've said is true. So please make sure you do give them a try, and they're very useful to allow you to keep track of what we're doing. So far we've talked about eigen functions and eigenvalues, and my statement previously in the discrete system that we were looking at was that I get a set of orthonormal complete eigen functions, which will form a basis for any function. So I can expand functions in these in this eigenbasis. A similar thing happens here, and I've written down a set of eigen functions, and you can check that the eigen functions are in fact orthonormal. I've normalized it now with this factor of 1 over root L, and you can calculate the standard inner product and show that they're orthogonal as well. So they're an orthonormal set. And all that's remaining is for me to tell you what it means to say that the eigenbasis is complete. And in this case, completeness means the following. Completeness means that I can write for my eigenvectors that the sum over these integers n of 1 over L e to the I k n x e to the minus I k n x prime. And if I sum over all of the n's, this will give me the Dirac delta distribution x delta of x minus x prime. Okay, and this holds for values of x and x prime in the interval that we're looking at between so this is for x and x prime in the interval between minus L over 2 and L over 2. Right. So the thing to notice here is that at the end of the day, we put a cutoff on how big our interval is, but at the end of the day, we want to send that cutoff off to infinity. So we want to take L to infinity. And if you look at the set of eigenvalues that we had, these kn's, right? Notice that I'm dividing through by L here. So as I make L larger and larger and larger, in fact, the spacing between eigenvalues goes to 0. So this is why, for example, I said that we're talking about a continuous spectrum. The continuous spectrum says that the spacing between eigenvalues, between separate eigenvalues, is 0. It's a continuum. Okay. So let's make a note of that. Note that as L goes to infinity for the real line, for the whole real line, the spacing between adjacent eigenvalues, Kn, goes to 0. Hence, we have a continuum of eigenvalues, or continuous spectrum. In this limit, the following is true. The sum over these integers of whatever it is we were talking about goes over to an integral over the real line from minus infinity to infinity dn of whatever it is we're talking about. By that I mean the following. N, in the discrete case, when we put a cutoff and when we compactified the interval into a circle, N was a discrete number, 1, 2, 3, 4, etc. In going to the continuum, I have to analytically continue N so that I allow values, an infinity of values between, let's say, 1 and 2, or 2 and 3, etc. So in that case, the sum becomes an integral, and the summing over N becomes an integral over N. So typically, this is not really cast as an integral over N. This is usually phrased in terms of an integral over momenta dk dn by dk. Notice that k was a function of n, so I can invert that relation and get n as a function of k. And if I change variables from n to k, so then I can write this as an integral over the eigenvalues themselves. In this case, the eigenvalues have an interpretation as momentum in the physical problem we're studying. And this quantity dn by dk is what we call the momentum density of states. So dn by dk is L over 2 pi, is the momentum density of states. Okay. And here we have analytically continued n. Okay. Another convention that I need to point out and that's important in this game, is that we usually phrase things not in terms of an L-dependent, by which I mean this, some L-dependent momentum density of states, but in fact in terms of an L-independent local density of states. And we get the L-independent local density of states by dividing through by L, the size of the interval. Okay. More generically, if we go to higher dimensions, I divide through by some power of L. In other words, I take my system, I put it in a box, and then I divide through by the volume of the box. Okay. So in this context, we phrase things in terms of a local density of states. Which is L independent. And write as in fact, let's write it as dn by dk as rho of k, or another way of writing that is rho of lambda, the eigenvalues, is dn by d lambda, which is L over 2 pi root lambda when we convert it to L's. And in the continuum limit, as L goes to infinity, the completeness relation implies that the integral from minus infinity to infinity of dk over 2 pi e to the I k x minus x prime is equal to Kronecker delta. Right. And notice that in this case, the length of the interval L has disappeared. Okay, so there's two things to note about this. Let's firstly make a let's firstly highlight it. This is an important relation, and there are two things we need to note about this. The first is that this is an L independent relation. And the second is that it's nothing but the Fourier representation for the delta function. Okay, so something should be bothering you at this point, which is I've taken the system on an infinite line, on the real line. I've put bounds on the system from minus L over 2 to L over 2, and I then imposed boundary conditions. So in particular, I've imposed periodic boundary conditions on this, so compactifying that interval into a circle. And I've deduced a whole bunch of things from it. I've given you a delta function representation, Fourier representation for the delta function, etc., etc. And you should wonder, how dependent are these results on the boundary conditions that we impose? Now, periodic boundary conditions are certainly not the only boundary conditions we could impose. We could impose Dirichlet boundary conditions. We could impose Neumann boundary conditions. We could impose mixed boundary conditions, all of which, are perfectly natural in terms of a physical interpretation for this problem. But how dependent are our results on these boundary conditions? So let's ask the question, and then we'll try and answer it in the next slide. So how dependent is all of these things we're talking about on the type of boundary conditions we impose? Okay. So suppose instead of the periodic boundary conditions, we choose to impose Dirichlet boundary conditions. So the Dirichlet boundary conditions look like this. And I'm going to say that I'm going to say that I'm going to choose that phi equals 0 at the boundaries, the same boundaries now, at x equals plus or minus L over 2. So suppose we choose that phi equals 0, the eigenfunctions vanish, the solutions of that differential equation vanish at x equals plus or minus I over 2. So another quick calculation. And I would like you to show that, by which I mean solve the differential equation, that normalized wave functions, eigenfunctions, so solutions of the free particle equation of motion are that chi n of x is sine of k n x plus L over 2, where n equals 1, 2, etc. Show that these guys are normalized eigenfunctions. For the free particle. So again, I'm going to leave you to show this, and we're going to take it that you will do it, and I'm going to use the result now.
Can I ask a quick question regarding that?
Yeah, go for it.
Is the knx plus L over 2 all an argument of the sine function there?
Yeah.
Cool.
So like that. Yeah.
Yep, thank you.
Good. And where kn, the kn are now given by n pi over L. Okay. In other words, the kn's in this case are half as much as with the periodic boundaries that we found. So if I impose Dirichlet boundary conditions, the values of the kn, the values that the kn's can take are a factor of 2 different from what we got with periodic boundary conditions. But in this case, I will find that the momentum, the eigenvalue density of states can be written as of states are given by rho of lambda equal to dn by d lambda, which comes out to L over 2 pi, and I would invite you to show this as well, L over 2 pi root lambda. The point here is that even though the kn's are not the same as with periodic boundary conditions, when I calculate the eigenvalue density of states, they come out to be exactly the same. In other words, the number of states per unit energy, per unit volume, is independent of the boundary conditions at infinity. So that's the takeaway message from here. It's an important enough message that I'm going to write it in a different color. So the number of states per unit energy per unit volume is independent of the boundary conditions at infinity. In principle, I only gave you 2 data points from which to make this statement, but I've actually told you enough that you may be able to already put together enough to make a more general, to convince yourself that this is a general statement. Okay, so that's roughly all that I wanted to say about this section. What I wanted to do next is, I didn't actually think I'm not sure why, but I didn't think we'd cover all of this so quickly, but here we are. So we've discussed that, we've discussed the Fourier representation and the density of states. So what I want to talk about next is the next section, which is on integral representations and differential equations. Can we take a 2-minute break? And I just want to get a cup of coffee, and I'll be back, and we can pick up from here, okay? Let's start again. Right. So by now, you've all probably built up a substantial set of tools and techniques for finding solutions of various differential equations that you've encountered already from your first year at university. One very powerful, okay, so I should make one more statement, which is that in physics and in mathematical physics in particular, we're kind of interested in tools that are not tools that you use for a very narrow purpose. The more powerful a tool is, the more, rather, it's the opposite way around. The more universal a tool is, the more powerful it is. So we're not looking to build spanners. We're looking to build Swiss Army knives. Okay, we want to find powerful universal tools. for solving as many problems in as many classes of differential equations as we possibly can. One very important tool, one very powerful method of solving differential equations is by series solutions. So if I have a differential equation for, let's say, y as a function of x, what I do is I make a power series expansion of my function, and I substitute that back into the differential equation and hope that I get sufficient conditions from the differential equation and its boundary conditions that I can restrict the coefficients in this power series expansion. This is what we call Frobenius's method of power series solutions to differential equations. Now, once I get a power series expansion, I'm not entirely guaranteed that this will be the solution of my differential equation. And in fact, it only is the solution of the differential equation if that power series converges. Now, convergence, if you had to ask what is the difference between a mathematical physicist and a theoretical physicist, the answer is that theoretical physicists will assume that the power series converges and the mathematical physicist would check. So the convergence of a power series solution is in fact a very, very important thing in getting solutions to differential equations. We tend to assume that, as long as some conditions are met, the power series always converges. But in principle, you really ought to check every solution that you find by the Frobenius method against its convergence. Sorry, I lost my Zoom screen. There we are. In this section, I want to take things a little bit further and ask how, if at all, the analytic properties of the solutions of the differential equations are related to the coefficients of the differential equations. So here's the question that we would like to pose here. Right? Maybe the answer is that it's not related at all and we're grasping at straws, but maybe it turns out that there's a lot of information that sits in the coefficients of the differential equation that we're trying to solve that I can read off about the properties of the solutions without actually solving the differential equations, right? I'm going to assume that you, like me, are inherently lazy and you'll avoid solving differential equations if at all possible. Like when the first time you solve the logistic equation, turns out you don't have to solve the logistic equation. You can read off the properties of the solution, the long-term properties, etc., by just staring hard enough at the differential equation. And in fact, what you're doing is you're staring at the coefficients of the differential equation. This is not an art, it is in fact science, and we want to make it more precise in this section. So the question I want to ask here is, how are the analytic properties of solutions to differential equations its solutions related to the coefficients of a differential equation. And the caveat here is I don't know whether they're related at all. Okay. A priori. So here's where complex analysis comes in. Analyticity, it turns out, is a property that is best dealt with on the complex plane. So whenever you see statements about analyticity, etc., you should always think in terms of the complex plane or functions defined on the complex plane. So analyticity is a property that is best defined on the complex plane. And to illustrate, let's do an example, right? So I want to consider a very straightforward differential equation, which you can all by now solve in your sleep. So let's consider the differential equation. The first order ordinary differential equation. Let's say u by dx equal to u squared. It's a separable differential equation, so it's straightforward, but you can also just ask which function that when I differentiate it results in the function itself, in the function itself squared, and you would realize that you're looking for a function that goes like a negative power, and in fact it's got to be 1 over x with a minus sign to take care of the minus sign that comes from differentiation. So this is solved by the function u of x equal to minus 1 over x, as you can check quite straightforwardly. And this is a solution everywhere except at the origin. Because at the origin, 1 over x blows up. Technically, I have two branches of solutions, one defined on the negative real line and the other one defined on the positive real line, right? And if we just constrain ourselves to thinking about real solutions, u of x, then these are two distinct branches of solutions that I cannot connect. There's no way to connect the region x less than 0 to x greater than 0 unless you go through x equal to 0 here, in which case I have these two distinct branches of solutions. So this results in two distinct, or let's say disconnected branches of real solutions. So as long as I'm restricting my attention to real valued functions, I will have these two disconnected branches. Okay, there's no way to connect them unless I go through x equals 0. If, on the other hand, we considered not real solutions, but we allowed ourselves to consider complex solutions, if we considered instead the complex equation and I must stress here, we're solving a rather trivial problem. But we're trying to just build some intuition for what's going to happen with less trivial problems. So I want to consider now the complex differential equation dw by dz equal to w squared, right? Here we would find that w of z equal to minus 1 over z is a solution which is analytic everywhere except at z equals 0. And you can show this by taking w of z equal to -1 over z and showing that it satisfies the Cauchy-Riemann conditions that guarantee analyticity everywhere except z equals 0. Of course, you could just look at it and see that it's a holomorphic function. In other words, it depends on z alone and not z and z bar everywhere except z equals 0. So that is analytic everywhere on C less the origin. Okay. However, in this case, because I'm not restricting myself to real solutions, if I puncture the complex plane by removing the point x equals y equals 0, I don't destroy the connectivity of the domain of w. Okay. And this is because I can always connect x less than 0, the real part less than 0, to x greater than 0 by just going around the origin. Okay. So this still has a connected domain. The domain is not simply connected. In other words, I can draw a circle around the origin, which I cannot squeeze to 0. I cannot squeeze that circle to a dot without cutting the circle. So this domain is called not simply connected, but it is nevertheless at least connected. Okay. More generally, look at the differential equation. Let's say dw by dz minus gamma over z w equal to 0, where gamma is some real parameter that I'm allowed to dial. And I'm going to call this coefficient here I'm going to call this coefficient the coefficient we'll call P of Z. And that's just minus gamma over Z. So the key thing about this coefficient is that it is it's got simple poles at Z equals 0. A simple pole at Z equals 0. Okay. Again, you can take this differential equation, forget about the fact that it's a complex differential equation, and write down a solution for the differential equation. And you'll find that the solution for this differential equation is simply w of z equal to z to this parameter gamma. And so depending on whether gamma is a non-negative integer, a negative integer, or not an integer at all, in other words, a real number or a rational number, the solution will have properties completely different properties. In particular, if gamma is a non-negative integer, so if gamma is 1, 2, 3, etc., then z equals 0 is a regular point. There's nothing particularly funky that happens at z equals 0. On the other hand, if gamma is a negative integer, -1, -2, etc., then I've got a pole. The pole is simple if gamma is -1. It's a higher order pole if gamma is -2, etc. Or if gamma is, let's say, a half, in which case my solution is the square root of gamma, then I have what's called a branch point at z equals 0. The point here is that clearly the parameters in the differential equation, this gamma, which is just a parameter in the coefficient of the differential equation, are actually determining the analyticity properties of the solution. So let's summarize that. Depending on whether gamma is, depending on whether gamma is non-negative integer, negative integer, or non-integer, so an example here would be something like 1, 2, etc. Here, -1, -2, etc. Here, the canonical example would be a half, etc. The solution W of z has a regular point, a pole, or a branch point at z equals 0. And the moral of the story is that the parameters of the differential equation determine the analyticity properties of the solution. So the parameters of the dE determine the analyticity of the solution. So without actually solving the differential equation at all, and again, I grant you that this is a rather trivial differential equation, but the lesson that we're learning from here is actually universal. Without actually solving the differential equation at all, right? By just staring at the coefficients of the differential equation, we're going to be able to say whether or not the solution at a particular point is regular, has a branch point, or a pole, and even the order of the pole by just looking at the coefficients of the differential equation. So I hope you can appreciate how powerful a statement this is, right? So in this case, I solved the differential equation by inspection because it is a trivial differential equation to solve. And my claim is that the lesson that we learn from this trivial differential equation is, in fact, a universal lesson. And it's a universal lesson that is just universal enough that it is one of these powerful tools like the method of Frobenius. Okay, so I want to stop there for today. I hope I've conveyed some intuition, at least, for where we're going with this. And on Thursday, we will make more general statements for general first order linear differential equations, and I'll do some examples that show how all of these things work before we move on to where we really want to go, which is second order differential equation. Any questions?